You see a workflow platform like n8n connect dozens of apps with a few clicks, and it feels like a natural bridge to physical robots too. But that visual ease masks a deep engineering chasm between software logic and mechanical reality. Today we unpack why the gap exists, how latency and safety constraints break simple automation links, and what this means for the future of intelligent machines. The promise of platforms like n8n is compelling. Connect any API, run custom code, and orchestrate complex tasks without writing a single line from scratch. The visual builder feels intuitive because it treats data as fluid streams that flow endlessly between services. When you move an email or sync a database record, the system handles failures gracefully with retries and timeouts. But when you try to apply this same logic to physical hardware, the rules of engagement change entirely. Software runs in virtual environments where time is elastic. Robotics operates in a world governed by physics where milliseconds matter more than elegance. The first critical distinction lies in how these systems handle timing. In pure software automation, n8n functions as an orchestration layer for data flows and API calls. It prioritizes throughput and reliability over deterministic speed. You can afford to wait seconds or even minutes while a database locks up or a third-party service pauses. However, real-world robotic control demands sub-millisecond latency guarantees to close feedback loops with physical actuators. If a robot arm is moving at high speed and encounters an unexpected obstacle, the system must stop within milliseconds to prevent damage or injury. A workflow engine designed for cloud APIs simply cannot provide that level of deterministic timing without significant custom engineering underneath. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This leads us to the second major hurdle: stateful context. Visual coding platforms abstract away the messy reality of execution environments to make building easy. They assume a clean start, predictable inputs, and infinite retries if something fails. But physical machines are never in a perfect vacuum. A robot arm experiences mechanical drift over hours of operation, sensors introduce noise into every reading, and environmental conditions change constantly. In software automation, a failed step is usually just a retriable error state. In robotics, that same failure could mean a collision or a lost position that requires complex recovery logic far beyond simple conditional branching. The platform does not inherently track the physical state of the machine because it was never designed to understand torque limits or joint angles as critical variables in its decision tree. We also see this gap widen when we look at agentic reasoning and safety validation. While large language models can generate code for robot movements, they cannot inherently validate physical safety constraints on their own. An LLM might suggest a path that works perfectly in simulation but exceeds the torque limits of a motor or creates a collision risk with nearby equipment. Without external middleware specifically designed to enforce these hard boundaries, there is no mechanism within standard workflow platforms to catch these errors before execution begins. The architectural gap lies here. General-purpose automation tools lack the specialized safety interlocks required for embodied systems. They can tell a robot what to do in theory, but they cannot guarantee that doing so won't break something or hurt someone in practice. This is not a failure of n8n as a product. It is an architectural boundary shared by most visual workflow platforms. The tool excels at its intended purpose, orchestrating software processes and data flows across the cloud. But extending these tools into robotics requires significant custom engineering to bridge the divide between logical workflows and physical constraints. Practitioners who attempt this extension often find themselves decoupling the AI logic from hardware execution, building a separate layer of middleware that handles real-time control while using n8n only for high-level task planning. This effectively acknowledges that visual coding tools are not yet ready to be the primary controller for complex robotic systems without substantial modification. The industry is moving toward agentic frameworks that attempt to bridge this gap by combining LLM reasoning with workflow design in unstructured environments, but these remain distinct from standard automation platforms. The trade-off remains clear: you gain ease of use and rapid integration at the cost of physical determinism. As we build more autonomous systems, understanding where software ends and hardware begins becomes crucial for safe deployment. We cannot simply plug a robot into a workflow engine and expect it to work. We must engineer the interface that translates logical intent into mechanical action with the necessary safety guarantees. The future of intelligent machines will likely involve hybrid architectures where visual platforms handle high-level coordination while specialized control systems manage low-level execution and safety validation. This separation ensures that the speed and flexibility of software automation do not compromise the physical integrity required for real-world operations. As we push further into autonomous robotics, recognizing these fundamental constraints is essential for building systems that are both smart and safe. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.